Hello everybody, welcome to this lecture 2 of week 1 on the course of control engineering. My name is Ramkrishna. I'm a professor of electrical engineering at IIT Madras. In the last lecture we concluded by listing out various components of a control system. Right? It had a plant, it had a controller, a disturbance signals, there were reference signals, output signals, and so on and so forth. And we left the lecture by saying that the next key step is to understand how a system works before we can do something with it, before we can give some control signals to it or design a controller and so on. So in this we will start by understanding behaviors of systems, and based on certain input-output relationships we will try to classify systems in several aspects. So to begin with, what are the key aspects of a system that we need to understand? The first thing would be the dynamics of the process. And here when I say process, I say a system, I say a plant, everything would kind of mean the same, right? So we'll use that interchangeably. So the dynamics would be of how the system evolves over time, right? So how possibly the temperature pattern evolves during the day, during a winter day or a summer day, or even things like how fast my air conditioner responds to a signal, how fast does it cool down my system, and also the steady state response. We'll classify both of this in this coming lecture. There will also be physical constraints, right? So for example, my car can only go at say 120 or 140 kilometers per hour, or my motor can only exert a certain torque, and so on, or my battery can supply only so much energy or so much power. We will also ask ourselves and try to analyze how does a process respond to an input. How does it respond to disturbances, right? If I am traveling on a straight road at say 60 kilometers per hour, if I encounter a uphill or a downhill, how does my controller, if at all, automatically adjust its speed? And to do all these things, we will use the language of mathematics and develop mathematical models. And we'll soon see how mathematics is a perfect tool to explain about the physical world. And once we have those explanations, we can again use math to design control laws finally before we go to implementation of these controllers. And why are we obsessed with math, right? We all grow up learning physics and several experiments of physics, starting from the romanticized version of the apple and Newton to stories which Galileo did while studying about gravity, how Kepler's laws came into picture by mere observations, and also things related to the Archimedes principle, the density, and when a body is immersed in a liquid, and so on and so forth. So those were all experiments which were something which we discover phenomena around us, or we try to make some things behave in a certain way, right? And that's what we say, that physics is mostly like an experimental science and a part of natural science. And much of the experiments, if you see some other stories of something accidentally invented or discovered as an experiment in a garage and so on. So in this world of physics, mathematics is of course a part of physics where experiments are cheap, where we use mathematics to argue why a system behaves in a certain way. We use mathematics to also therefore learn the behavior of the system under different conditions, different temperatures, different pressure, different inputs, and so on and so forth. So the system that I will broadly talk about here is a collection of components. I'll call them kind of it could be physical, it could be biological, or any other components which together perform an intended objective. For a given input, we also will call that as excitation. The system will give a certain output. Like if I press my accelerator, my output is in the form of velocity when I am driving a car. So systems could be as simple as just one input and one output. I switch on a bulb, it throws me light. Output is the light, input is the electrical voltage. Simple system. System can also be a collection of multiple subsystems. So, say suppose I want to do a complicated operation involving a motor which will generate electrical energy, which will convert electrical energy to some kind of a rotational mechanical energy, that through some gears I can transmit power and do some kind of a mechanical operation like a, I don't know, like a lathe or anything like that. So, system could be collection of multiple subsystems also, and each subsystems will have their own properties, and I can now see the larger system as some kind of connections of smaller systems, and therefore my understanding at the micro level, if that is good, I can generalize it to the overall collection of these subsystems. Again, I will again classify them as a given output till a given given input or excitation to a given output or a certain response. Okay, so suppose, and we all are aspiring to be electrical or electronics engineers. The simplest of all circuits is the resistor circuit, or circuit or a resistive network as they call. So suppose I have a circuit that's shown here. Say the input is say about 20 volts, and say I want to measure what is the voltage across this. I'll call this as VR2. Okay, so based on simple voltage division formula, if I will call this as input, and this VR2 I will call this as output. So this input voltage generates certain voltage across R2. You could also measure current. There is nothing that stops you from calling current as the output. Okay, so when the input is 20, the output is 15. Okay, now not surprising. It's the moment the input goes to from 0 to 20, the output also goes from 0 to 15. The moment my input drops now to 10, the output also automatically drops to 7.5. The input is 0, output is 0. Again, if I maybe get my input to say some other level of 15 volts, the output also immediately changes as per the voltage division formula. Similarly, now if I, okay, it's not the most beautiful of animations, but good enough to understand. So if I switch on a bulb, it gives me light. If I switch off, it immediately goes off, right? So in this case, the first observation is that the moment I give V1, VR2, moment I give V1 as 20, VR2 goes to 15 and so on, right? The output becomes 0 as soon as the input goes to 0. The output switches to a new value instantaneously when the input takes a new value. That is what happens, right? So here the input goes from 20 to 10, and the output immediately takes a value which goes from 15 directly to 7.5. It goes from 15 to 0, output also instantaneously becomes 0. Similarly, here it goes from 0 to 15, and the output also adjusts accordingly to I think about 12 volts or something like that. Okay, why am I saying this so specifically? Is there something else that we could also observe? Okay, so maybe I'll just do this example. Okay, again may not be the best of animations, but say good enough. So I just try to switch on a fan. It slowly is building up speed, whereas if I just say check the bulb on the background, it is the switch is on, the bulb is on, the switch is off, the bulb is off. So what this fan does is it starts at some initial, it starts at a 0 speed, and it slowly builds up speed to its full value, depending on if my regulator is at position number 1, position number 2, position number 3, and so on. What also happens is when I switch off the fan, it does not immediately come to rest. It takes some time before it goes to rest or 0 speed. So what we observe here is that while the bulb switches on and off instantaneously, or while the bulb switches on instantaneously, the fan takes some time to reach its desired speed. So now we have three things, right? So we have the 0 speed, and then we have, I just call this as number 1, say the full speed. And it usually takes some time. So this is my initial condition, this is the rest. When it reaches full speed, I call it the steady state, and in between when it goes from 0 to this full speed, this I will call as the transient. Also loosely I can call it, say, some kind of a temporary behavior. The steady state is the behavior which I would actually want the system to go, and it takes some time to go from the 0 speed to the steady state speed, and that transition I will call as the transient. Okay. Similarly, when the fan is switched off, its speed gradually decreases to 0, not instantaneously. Okay. So I'll go one slide back and check what happens. How do we visualize this in terms of circuits that we know? Okay. So we all know resistive circuits by now. If I am just have a certain input voltage, the output takes certain value. So here I am just measuring, say, the current, right? For a V of 20 volts, for a R of 30 ohms, I will have certain I which will be V over R, or 2 over 3. Okay. So the voltage, so I switch on, it is 20 volts, the current is about somewhere between like 600 milliamperes, or 666 to be precise. The voltage goes to 0, current goes to 0, voltage is again back to 20 volts, the current is instantaneously back to 666 milliamperes. Okay, what happens in a circuit when I just put an inductor in addition? So the voltage goes from 0 to 20 when I switch on, on the switch. The current, you see, doesn't go to 666 instantaneously, but it takes some time, it slowly evolves. Similarly, when the voltage goes to 0, the current immediately doesn't go to 0, it takes some time before it goes to 0. And similarly, if I just switch it on again, it takes some time to achieve its value. So these things, these are the transient, and when it reaches its final value, this is called the steady state. Of course, we will do a little more analysis on this to actually quantify this, and maybe say why is this a certain value, how fast it goes, why doesn't it go maybe a path like this or some other path. Okay. Similarly, when I switch it off, it doesn't, my steady state, if I switch it off, the fan, the speed would be 0, or in this case the current should be 0, and it takes some time. So this is again the transient, and when it reaches 0 speed, I will call this as steady state, and so on. Okay. So the behavior that we observe here is similar to that of a fan. Now with here I am talking not in terms of speed, but in terms of how the current builds up in that circuit. Which means that if I now talk of systems or a plant or a process as certain input to output relation, voltage is the input, voltage is the output, or voltage is the input, current is the output, voltage is the input, speed is the output, and so on, or maybe voltage is the input and the air conditioner pumping in cold air as the output, and so on. I can now classify these systems as static and dynamic, and we will see why we call each of these in this way. Which one will classify as static, which one will classify as possibly you can already think of this. Okay, so static system, a system whose output at any given time depends only on input at the same time. V equal to IR. Say R equal to 1, V equal to 1, I will immediately be equal to 1. V is 0, I is 0, V is 2, I is 2. So I also call these systems as being memoryless, that the system has no dependence on the past inputs or states. Whatever is the current input will decide the current output. Okay, so some quick examples. If I just talk about water flow of a water network, there is some input and it's being distributed to homes across these pipes. So a nice relation will describe the how the system behaves, that whatever is the inflow in the water will be just the outflow. If I have one more pipe here, say I'll call this as QO3, where the water is flowing out, this will add up here. Maybe if something else is feeding into this, I'll call this as QN2, this will just add up here. Whatever is the inflow is equal to the outflow. So in this I can write this simply as inflow, the net inflow is equal to the net outflow. Of course, in an ideal world there will be some losses also. Okay, we'll talk of this when we need. Similarly, if I were to look at an energy distribution network, right, say at the substation there is some energy or some power, whatever which is being measured or consumed, and this is say E2 and E3. Whatever this energy meter will record should be equal to E2 plus E3. Again, because there could be some losses. Similarly, I go one level down and I say, well, I have like say maybe this is my substation, this is my residential area or the apartment where I stay, and say these are these two houses. So a meter or the power which is consumed at the whole of the apartment would be whole of the apartment or the building would be equal to the each individual consumption. Similarly, E3 will be equal to E6, E7 and E8. Okay. So I just know that whatever energy is being consumed here is equal to the sum of this and this. This is equal to the sum, 2 is equal to the sum of 4 and 5. If E4 is the energy meter recording here and E5 is the energy meter. Similarly with E3, E6, E7 and E8. Or in general I can also write a larger law as E1 will be equal to E4 plus E5 plus E8. Okay, what could happen in this case is the following, right? You can now kind of think of some problems that we could solve, assuming the losses are very small. Say there is some kind of a power theft happening somewhere. You know that, okay, so E1 may not be equal to E2 and E3 when there is maybe somebody is trying to steal power from here. Or say some meter doesn't function, right? So if E5 is not functioning, I can go back and say that, okay, I don't have a recording of E5, but I have E2 and E4, so I can recover the recording of E5 by looking at the recording of E2 and E4 and so on. Okay, so all these things here is that if in the first example, if there is no inflow, there will be no outflow. Okay. Similarly here, if there is no energy being consumed here, there is no supply here, all E2, E3 will become 0. If E2 is 0, E4, E5 will become instantaneously 0 and so on. So this is how we could write a static system. So by definition, the output depends only on the input at that time, and I also call them memoryless because it just doesn't remember what happened in the past. It just acts to the current inputs. More example, you can look at the spring Hooke's law, which is generally written as F equal to Kx. Okay, I am just not messing up with too much notations. We'll just stick to plus K, and when we need, we'll see why it is minus and so on. Ideal transformer, it just transforms energy from one circuit to the other. I'll do a little more detailed or a little more elaborated expression on this. Economics, if I look at a simple interest formula relating the principal to the interest, principal is 0, interest is 0 and so on, or also depending on the term, on the number of months or years the interest is calculated. From engineering point of view, we all would know how an operational amplifier works. So one of the way it can work is a summing amplifier. It is used to combine the voltages V1, V2 and V3 into a single output voltage depending on R1, R2, R3 and therefore the RF. In all of this, if V1, V2, V3 goes to 0, V out goes to 0 and so on. So I can call this as static systems. Input, the current input decides the current output. The past input does not define the current output. We will not talk of future inputs as yet. Okay, so now therefore if I now classify or call something as dynamic systems, the definition should violate these two things here, right? Output is not only depending on the input at the same time, but it also depends on the past behavior or the state. So if I switch off a fan, it does not come to 0 instantaneously, right, because it stores, physically it stores some kinetic energy or some rotational kinetic energy, and slowly the energy gets dissipated through some friction and the fan comes to rest. Okay. Similarly, when it goes from 0 to a steady state speed, right, it does not really happen instantaneously. It depends on certain system parameters for it to go from a 0 speed to a speed of 1. So the output not only depends on the present input, but it also depends on the past input and the state. And when I say state, it would mean that if I am looking at say for example the speed here, right, the speed, the initial voltage is, so okay, if I just were to draw the speed profile, okay, I am assuming this is visible here, and say this is my steady state speed, or when I just switch off the fan. Okay, so if my so this is how my speed pattern or speed thing would behave with time. Okay, here I am just, then my switch turns to on. Okay, but however, if my fan is already in this speed, say suppose I just try to rotate it by hand, okay, and my speed is this, it will continue to be in the same speed. There is no transient that happens, and therefore I say it depends on the past inputs as well as the past states. If it is already at that speed, I switch it on, it will just continue to be at the same speed. On the contrary, if I try to with my hand, I try to rotate it with a higher speed, it might just come down again to its to the steady state speed. Okay, and therefore I say it depends not only as a past inputs, but also on the past states as well, present and past inputs as well as the states. The states evolve with respect to time due to, of course, input signal. It could be certain external perturbations or even naturally, and therefore I call these systems as systems with memory, that they store some information about the past inputs and system states. If the initial state is 0, nothing happens, it just stays at 0, and we can see this as examples in capacitors, inductors and simple pendulum. So the circuit which we had an inductive element, and therefore it took some time to build the current, and it also took some time to get the current to 0 as soon as the input was switched off. And these are typically modeled using differential or difference equations. And largely in this course we will stick to differential equations. We will not touch much upon difference equations. So how do we write these as equations? We know the relation between voltage and current for a capacitor. I can also write this as a differential equation of I equal to C dVc by dt. Similarly, I have a circuit with if it's an inductive element, I know that the voltage and current are related by V equal to L di by dt. And if I go back to the original circuit that I had for simulation, I had a V1 here, R1, L1 producing a current I1. I could just write this as simple Kirchhoff's voltage laws as V equal to R1 I1 plus L d I1 by dt. And of course, now I have a differential equation, and the solution of this differential equation will give me a plot or a behavior which will exactly look like this. Again, we will come to that a little later. This is just to understand how systems behave, and the details will follow in the coming weeks. Okay, similarly, I can now look at even examples from other domains, like some mechanical domain. First order heat equation. I cool off an object. If I am ironing my clothes, I switch off the power supply, the iron box, the temperature does not go to 0 immediately. Similarly, if I switch off an induction stove or something like that, or I switch off a fridge, the temperature doesn't go to 0 instantaneously or to the room temperature instantaneously, right. So, the temperature, what does it do? Say my iron box is at say 70 degrees Celsius, or even a bucket of hot water. Say if it has 80 or 100 degrees Celsius, the ambient temperature is say 30 degrees Celsius. These objects, they kind of interchange heat among themselves, like the bucket of water with the environment or the hot iron box with the environment, and eventually it will settle down to its environmental temperature. Again, it does not happen instantaneously, it happens over time due to heat exchange with its surroundings, and in the steady state the temperature of that object will equal to the will be equal to the environmental conditions. This K will depend on lot of factors of how much energy or heat the that particular object can store. For example, you have a pan which makes dosas, it has this capacity to store heat for a little longer time, and so on. Okay, so this is a kind of good classifications. We can conclude by just recollecting what we learned so far. In static systems, the output depends only on the current inputs, not on the past input or the state. Dynamic system, it depends not just on the current input but as well, but also on the past inputs and states, and therefore we call them as systems without memory for static and systems with memory for dynamic. And these are time independent in the sense that the evolution is just instantaneous. I switch on, I see the output, I switch off, the output disappears, whereas in a dynamic system, the system response evolves with time. The moment I turn an air conditioner to 24 degrees, it takes some time for the room to cool down. In the static system, I only see steady state behavior. It goes from 0 to 1 instantaneously, whereas the dynamic systems exhibit both transient and steady state. And the transient is what we called as the emerging behavior from 0 speed to full speed, or some say 25 or 28 degrees to say 21 degrees and so on. Okay, so good time to see where we are and ask ourselves some questions. Think of it, it's a single tank system, a static or a dynamic system. You may also have to keep this in mind before you classify those as a static system or a dynamic system. Coming up, we will see a little more classifications. Stay tuned. Thanks for listening.